Welcome back. This is the third and likely the last segment in section 1.2. I think we can probably get everything we need to get done with the video. It may run a little bit long, but I think we're okay on time. So rather than sitting here bloviating about something, let me get over to the document camera and we'll just start right in. So the first thing was just a quick reminder. We were talking about some geometry results about congruence and whatnot related to triangles. We discussed which sorts of arrangements lead to congruence. And I'm just going to, I'm going to continue just on the same sheet of paper. So we're still on page 5. So here's sort of a geometry result, and this should be very obvious. But if any two pair of corresponding angles are congruent, remember we're talking about triangles here, then the triangles are similar. Now this is just simply because the sum of interior angles equals 180 degrees. So if you got 2 of them on one triangle equal to 2 on the other, well, the remainder is just whatever gets you to 180 degrees, and so it has to be the same number. This is not a shocking result, but it's just something I wanted to state. Now, this one, on the other hand, is very important. And this is, in some sense, a statement of the fundamental theorem of similar triangles. It is the basis of, it is the mathematical basis by which trigonometry, in the sense that we will study it, is possible. Okay, and it has to do with the ratios of sides of similar triangles. So if you have, and so this is a geometry result, and I will refer to the fundamental theorem of similar triangles over and over again, but I'll just kind of use fundamental theorem similar triangles, okay? So here's the statement. The ratio of the measure of any two corresponding sides of similar triangles is equal. So you have to already have 2 triangles that are similar. And what this is saying is, if there's some, if you compare 2 sides that are the corresponding sides, so they're between 2 angles that are equal, this would be kind of the diagram here. So let's say here we have, you know, you have a triangle, and maybe here's a little bigger one. I know these all start to look like, you know, equilateral triangles, but it's just because it's easier to draw that way. So if we have, if we were to look at this side and look at its corresponding ratio, so this looks like maybe like 1.3 or 1.4 times, whatever, then the ratio from this side to that side will be the same number from this side to that side. So that if you can talk about, and it actually makes sense to talk about, like a scale factor, like how much bigger this triangle is than that one. Now the area will not have the same ratio, but the lengths of the sides do. And it turns out that the ratio of the areas is actually the square of that ratio. So if this is a 1.4, if this triangle is 1.4 times larger, then the area is actually, you know, 2.24, 2.2, 2.16, or whatever, 1.4 squared times the size. So let's look at, since I need a little bit more space to develop this idea, let's look at a couple of similar triangles. I think we're on page 6 now. And maybe not make them so equilateral, but here's a, let's make maybe like some obtuse triangle or something. So here's a triangle, and then here's a sort of a, well, a bigger triangle. It's not, I'm not a great artist. I don't claim to be. But let's look at some customary labels. So like I said before, it's very common to use a capital letter for the vertex of an angle. And for triangles, it's actually very common to use the name of those vertices as the points as well. So we'll call this A, B, and C. And then we'll call this one D, E, and F. Now, another sort of commonality, capital letters for angles and lowercase letters for opposite sides. So we'll have a lowercase a, lowercase b, lowercase c, even though you can't really tell the difference there, lowercase d, e, and f. So what the fundamental theorem of similar triangles is telling you is that provided that these two triangles are similar, which means that all their angles, corresponding angles, are congruent, if this is true, then the ratio of, say, one side to its corresponding side, so A over D, is equal to B over E, which is equal to C over F. And this algebraically is equivalent to flipping them all upside down. So D over A, E over B equal F over C. So this number is all the same number for these two sets of triangles. In some sense, this has a scale factor of whatever this ratio is. So you scale this one up by 1.2 or something like that. Now, here's where this gets interesting, is that if you rearrange this algebraic stuff and use these, there's actually 3 equalities here. You get a result which is A over B is equal to D over E, and A over C is equal to D over F, and B over C is equal to E over F. So what this is really saying is that within this triangle, right, there are some internal ratios, like the ratio of A to C is the same as the ratio of D to F. So this is kind of the lead-in to trigonometry, because you're saying, given the same value of an angle, whatever that angle happens to be, and of course this other sort of arrangement here too, that the ratio of this side to this side is actually equal to the ratio of that side to that side. And for those of you that have had a little experience with trigonometry, you get some, maybe this is starting to sound like SOHCAHTOA or something, where the ratios of certain sides are equal to whatever the sine, the cosine, tangent of these individual angles are, and there is a unique way to do it. And in fact, that is exactly what's going on. The trigonometric functions are representative of the ratios of certain shapes of triangles. At least that's kind of one way we can interpret it. It's not the only one. So I'm just going to put a pin in this and say, thus trigonometry. And just leave it at that. But since we're not going to develop too much out of this, it's just, I'll refer back to this result at different times. So this is kind of, at this point, we don't have any trig functions. We haven't talked about them. There's no need to. But what I will do is I'm going to describe a pretty simple problem involving similar triangles. So in the textbook, there's a couple problems I've assigned for this section that talk about eclipses and distances from here to here and there to there and whatever else. So let me just try to sort of, first off, I hope everybody understands that a solar eclipse is caused by a moon or something along those lines passing in front of the sun with respect to a viewer that's on the surface of a planet. So here's kind of the diagram. We've got, here's the sun, or any sun, and here's the sort of surface of the planet. And if I draw some visual lines here, if we had a planet, if we had like a moon or something that's sitting right about there, that I can create this sort of triangle shape that would block out all the, if you think about, if you're sitting right here at this point, you can't see the sun at all, right? Now, for whatever reason, it's like, I mean, people understand this picture, and you've probably seen it in, I don't know, like an earth science class or something else, but what does seem to be confusing is that if this moon is actually further away, then you don't get a total solar eclipse. What you get is you get kind of the moon sort of blocking out a little bit of the sun, but you know, you can still see some sunlight from all points on the surface of the sun, of the planet. On the other hand, if the moon is a little bit closer, then it actually blocks out more of the sun, and you end up with a wider area at any one time that can experience a solar eclipse. So the way that these problems are stated is they're either saying, I mean, ultimately, with all of these problems that are listed in the book, you're essentially having to figure out what that ideal distance is, and then make some decisions about whether the moon is further away than that, in which case there is no solar eclipse, or it's closer than that, in which case there is a solar eclipse, total solar eclipse. So that's kind of what every one of these problems is. There's two of them in there. So let me give some examples. Usually you have three parts of this, but I'm going to start labeling some things. So this is this sort of distance here is the diameter of the sun, right? And I think pretty universally, the number that the textbook uses is 865,000 miles. Let's say that this planet, just because I have the numbers handy here, how about the Earth? So the Earth, so we're talking about this distance is 94,500,000 miles. And let's do this. We'll have the diameter of the moon, and this is actually the moon, is 2159 miles. And we have this sort of distance that we don't know, which is the maximum distance away that the moon can be from the Earth in order for there to be a solar eclipse. Now, what's interesting about the Earth is that the Earth, Moon, Sun system is that the moon is kind of like in this really sweet spot where it is at almost just the right distance. So sometimes you have solar eclipses, which is where it's either at this point or a little bit closer. And sometimes you have what are called annular eclipses, where the moon is a little bit further out. And so when you see the sun with the moon in front of it, it looks like a big ring. And that's where, like, an annulus is the description of that geometric shape, a circle with the circle cut out in the middle. And so those are called annular, not like annular like every year, but annular is in the shape of a circle inside of a circle. So anyways, the problem as it's stated here is to find, well, what's that maximum distance X, and then maybe compare it to an actual, like an actual measurement. But anyways, so I don't want to overly complicate this problem. I just want to kind of set it up, because here's the thing. There are similar triangles here, right? And you have to, and I'm gonna use a little thinner pen so you can see it. So if you compare this triangle to this triangle, so this triangle goes all the way from sort of the peak of the sun down past the moon to the surface of the Earth, then back, bang. That triangle happens to be an isosceles triangle. And then you have this triangle from the moon basically doing the same thing. Well, those have to be similar triangles. They have this angle that's the same for, it's the same angle for both of these triangles. And then you have an isosceles triangle here, so these angles are equal to each other. Their sum of all three adds up to 180. Same thing with this triangle. It turns out that these are in fact similar triangles. In order to bring this x value in, you could do it, you could kind of split it down the middle so that you've got right angles out here, right angles here. But the result is the same. It's that if you take the ratios of the diameters of these two objects, they're equal to the ratios of their distances. So, or you could think of, you could divide it in half and you get the same thing. So if we're just looking at this upper triangle, say, right, the distance of this sort of one of the legs of the right triangle is equal to 94,500,000 miles. And the width here is twice the the radius here is one half the diameter. But you don't need to cut it in half because you're going to do the same thing with this one over here. So let me just write this ratio. So 94,500,000 miles divided by the diameter, 865,000 miles, okay, is equal to, well, that's kind of this situation where you're comparing two triangles together. And from the fundamental theorem of similar triangles, it says that the ratio of this side to that side, well, sorry, the ratio of this side to this side has to equal the ratio of this side to this side. So we'll have x over 2159. Now, what I've seen a lot of people do in the past is they get these mixed up. You just have to make sure that the corresponding sides are correct. And this is sort of the situation where that happens. Now, you might have a distance and then have to find a size or whatever else, but it's the manipulation of these two results. So algebraically, x will be equal to the product 2159 miles times the ratio 94,500,000 divided by 865,000 miles. And when you do this calculation, you're going to get some kind of goofy remainder. But and this is something I don't really expect everybody to know just yet. But there's this thing called significant digits and how many digits you should use and whatever else. I can just tell you that you should really only be using 3 digits. So when we round this value up, x, or round it off, x will be 236,000 miles. So this is about the distance from the Earth to the Moon, because the Earth does experience both types of eclipses. However, it varies. But this is sort of the upper limit. If the Moon's any further away than 236,000 miles, then you don't end up with a lunar eclipse. You don't end up with a total solar eclipse. On the other hand, if it's a little bit closer, then you do, or if it's exactly this number. Although exact is kind of a little bit vague there because you have a measurement error. But anyways, that's the that is the end of section 1.2. This is probably the hardest problem. I mean, for whatever reason, people just kind of struggle with this in this section. There's some homework problems associated with some of this stuff, and good